Okay. What we are going to do today is actually we are going through the derivations. We are going through the derivations. What is the first derivation we have to do? What is the first derivation we have to understand? We have seen some theory parts, some concepts in the previous class. Actually, it was a revision. And what is the first derivation we have to do? Just read the heading, which is the first derivation. In your class group, I have given you, or I have sent you personally some name of some derivation, right? Name of some derivation. The first one is electric field due to axial point of dipole. That's very important derivation. Electric field due to a dipole at an axial point. Electric field due to dipole at an axial point. Electric field due to a dipole at an axial point. Help me with this derivation in each step. First, what do we need to do? We have to construct a dipole. What is a dipole? What is a dipole, Betsy? Neha, Reham, everyone, look here. What do we need? First, we need a dipole here. What is a dipole? There is two charges, two equal and opposite charges separated by a small distance. That is a dipole. What is a dipole? Two equal and opposite charges separated by a small distance. Then this is the dipole. Here you have a minus q and here you have a plus q. This is two equal and opposite charges separated by a distance. This is the distance of separation between them. Now this is a dipole. What do you have to find out? You have to create an equation for the electric field at this point. You have to create an equation for electric field at this point. This point, let this point be P. This point be P. Now this point is P. There will be electric field at this point due to this dipole. How can you find out that electric field due to this dipole? There will be There will be electric field at P due to both the charges. There will be electric field due to both the charges at this point, right? There will be electric field due to both the charges at this point. You can place that in the next page. Now, what is the electric field due to plus Q? Electric field due to plus Q. Take a blank page. Take a blank page, and we are going to try out the derivations again. Okay. What is the electric field? What is the electric field at P due to this plus Q? Help me with this. That will be, how can I draw that? That will be away from the charge, right? This is a positive charge. So the electric field due to plus Q will be away from it. That means the electric field will be in this direction, that is E1. Got it? And what will be the electric field due to this minus Q? That will be in opposite direction. Right? This E2. So can we write just E1 and E2? E1 and E2. Let's try to write the E1 and E2. What is the next step? Do you have the note of that? Okay. What is the next step in it? You can write E1. Equation of E1, you can write it. What is the equation of E1? Electric field. What is electric field? Equation of electric field is force by charge, right? F by Q, force by charge. So that means due to plus Q, that will be away from the charge, and the value will be 1 by 4 pi epsilon naught, which is the charge here, Q. Q divided by distance square. Distance square. You have to take a distance here. You have to take a distance. Every distances are measured from the midpoint of dipole. What is it? Every distances are measured from midpoint of the dipole. So now this is the midpoint of the dipole. Now this is the midpoint of the dipole. Got it? And every distance has to be measured from the midpoint, right? So the point from the midpoint to this distance will be R. The distance will be R.
R is the distance between charges.
No, the distance between charges is 2a. We are taking it as 2a in the case of dipole.
Should we write it?
Oh, yeah.
No.
Write it again with us, with me. We are doing it together. We are doing the derivations together. Write it with me. Okay? The distance from the midpoint to the point P is termed as R. Okay? And what is the distance between the dipole or distance of the dipole is what? That's 2a. Now there will be a and another a in this side. The total you will get 2a. So this is 2a and the distance from the midpoint to this point P will be R. Got it? So what is the distance square? Distance from this charge to this point will be what? The whole distance is R and R is minus. You have to minus a from R, right? R minus a square. This is electric field, so you have to square it. This is electric field, so you have to square it. That's it. And which is the direction of this field?
P.
It is in the direction of dipole moment. That's from negative to positive. Minus Q to plus Q. So the direction should be in the direction of dipole moment. Direction should be in the direction of dipole moment. Got it? In the direction of dipole moment. So this is the first equation. Equation for E1. What is equation for E2? Help me with this. What is the equation for E2? 1 by 4 pi epsilon naught.
Q by.
What is the charge?
Q by R.
This is the charge. Q divided by. What is the distance? Distance from this point, midpoint to P will be R. And I have to take the distance from minus Q to P. That will be R plus A. Isn't it? That's R plus A. So R plus A the whole square. What is the direction of it? It is against the dipole moment. So it will be minus P cap. Minus P cap. Now you have two equations for E1 and E2. What is the electric field at P?
The net electric field.
Electric field at P. Net electric field. Net electric field at P. You can just take it as E. What will be E? E at P.
E1
E is equal to
E1
E1 plus
plus
E2. E1 plus E2. That will be
4
1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Q divided by R minus A whole square. Now plus what is this? 1 by 4 pi epsilon naught. Q divided by R plus A the whole square. And here you have P cap and here you will have a minus P cap. Right? Then that minus will be coming to the center. That minus will be coming to the center. Minus will be coming to the center. I will write it here. That minus will be coming to the center. Then what will be the equation? What will be the equation? E is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught.
Q by R.
Help me. What is the equation? 1 by 4 pi epsilon naught. Q divided by R minus A the whole square. P cap minus this minus is coming to this side. This minus is coming to this side, right? This minus is coming to this side. Then the equation will be what? Minus 1 by 4 pi epsilon naught q divided by what is on the denominator? What is on the denominator? R plus a whole square, right? R plus a whole square. R plus a whole square p cap. R plus a whole square p cap. Got it? R plus a whole square p cap. Now take out the general term or common terms.
Q by.
Yeah. Q by 4 pi epsilon naught is common here. So you can take out the term q by 4 pi epsilon naught, and inside the bracket there will be 1 by r minus a the whole square minus 1 by r plus a the whole square. Right? What is the direction? It is in the direction of p cap. What is p cap? Direction of dipole moment. What is p cap? Direction of dipole moment. Now you have to simplify this. You have to simplify this. How can you simplify this? Cross multiplying it, you can simplify it. How can you cross multiply it? R plus a,
R square.
R plus a whole square minus r minus a whole square divided by r minus a the whole square into r plus a the whole square. This is p cap. When you are expanding it, you will be getting r square plus 2ar plus a square. And minus of, should I do it here? Should I do it here, or can I write the direct term? Can I skip to the next part? When you are expanding it, you will be getting 4ar on the numerator. Is it okay? You will be getting 4ar on the numerator. Okay, so the equation will be q by 4 pi epsilon naught. On the numerator, there will be 4ar divided by r plus a into r minus a will be r square minus a square, but there are two of them. R plus a into r minus a into r plus a into r minus a. That means the result will be r square minus a square, and you have to square it because there are four of them as a total. So this is the equation. Now you can split this equation like q by 4 pi epsilon naught. You can split this 4 into 2 into t. So 2 into 2ar divided by r square minus a square the whole square. Now we have to do some assumptions and to do some substitutions. What is the substitution we have to do here? You can see the term dipole moment here. What is that? Q2A. That's Q2A. What is Q2A? Q2A is P, electric dipole moment. So you can write instead of Q2A the value of electric dipole moment, and there is a 2 also. And there is a 2 also. Where, what is that? There is a 2 also. Right? So 2 into Q2A. What is Q2A? P. P is Q2A. And there is an R divided by 4 pi epsilon naught. 4 pi epsilon naught. Or you can just write it in the common term like 1 by 4 pi epsilon naught. What is Q2A? That's P. P into R divided by P into R divided by, and the next one, assumption. What is that assumption? A is very less than R. That means this R square minus A square whole square is approximately equal to, approximately that to 0. That's approximately equal to this A square, very small value. A is very small value. When it is squared, that will be again a small value. So this whole term can neglect A. You can neglect A.
Two to eight.
There will be a 2. Q to A is P, so 2 will be there. Okay, that's all. And A is very much less than R. So from this term, you can neglect the term of A. You can neglect A. When you are taking out the A, there will only be R raised to 2, R square. R square in the inside the bracket. So R square all raised to 2. R square all raised to 2. That will be R raised to 4. So you can just write R raised to 4 here. And there is R on the numerator and R raised to 4 on denominator. So you can cut it out. R and R raised to 4 is cut out. And what are you left with? You will be left with this R cube. Okay. And what is the direction here? That will be P cap. Direction will be P cap. P cap. Okay. So the final equation for electric field at P will be what? That will be 1 by 4 pi epsilon naught 2 P by R cube P cap. Got it? This is the equation of electric field at a point due to a dipole at an axial point. This is the equation for axial point. Dipole, electric field due to a dipole at an axial point. This is actually in vector format. So this is a vector. What is the direction of this electric field? At an axial point, what is the direction of electric field? Towards P, what is P? Electric dipole moment. That will be from minus Q to plus Q. Got it? That's how what we can see here. What is this? What is this? What is this? This is P. P cap. What is P cap? Direction of dipole moment. What is direction of dipole moment? From minus Q to plus Q. So this is in the direction of dipole moment. Electric field at an axial point will be in the direction of dipole. Is that okay? Everyone, Arafat, Gobiga, Neha, Riham, Sidra. Is the derivation okay?
Yes, sir.
Okay. Should I repeat this or can I go to the next one?
You can move on to the next one.
Okay. Okay. Is it okay? The first derivation is okay. What is the second one? The second one. Electric field at equatorial point of dipole. The second one. Look at the second one. The second one. Electric field at equatorial line. Equatorial line of a dipole. Equatorial line of a dipole. For this, you need a dipole, right? You need a dipole. This is minus Q and this is plus Q. Minus Q and plus Q. The separation between them is 2A. 2A. This is the midpoint. This is the midpoint. Now this is a point P. This is a point P. At this P, there will be electric field due to both of these charges, right? I'm just showing the distance from minus Q and plus Q. Distance from minus Q and plus Q. Okay. And I'm taking it as X. I'm taking it as X. Okay. But every distance has to be measured from midpoint. Every distance has to be measured from midpoint of the dipole. So I have to draw the midpoint also. And that distance is termed as R. That distance is termed as R. This is the midpoint, so this will be A and this again will be A. Got it? And I am going to show you the electric field due to plus Q. Electric field due to plus Q charge will be away from it, along this line. So at this point, there will be an electric field E1 due to this plus Q. And electric field due to minus Q will be towards it. So along this line, there will be an electric field due to minus Q that can be called E2. Are you getting it? It is called E2. Now just try to write E1. What is E1? What is E1? Or there is a little data to be added. There is an angle theta here. Also an angle theta will be same on the both sides. There is an angle theta. Now you can find x from this. X is the distance between charge and this P, the point. What is x then? X square is what? X square is equal to, that's hypotenuse square. That will be base square plus vertical square, r square. What is x then? Root of this one. Square root of this one. Got it? X will be square root of this one. And x will be a square plus r square, all raised to 1 by 2. You can write square root of something like this. Square root of something like this. The number rise to 1 by 2. The number rise to 1 by 2. Gobiga. Gobiga, we just did this derivation. The first derivation. We did the first derivation. We did the first derivation, and the first derivation is the electric field at a point due to a dipole at an axial point. Got it? So here you have x here. Is it okay? Is it okay? You have the value of x here. Now you have to write E1 and E2. What is the value of E1? I am writing the value of E1 here. What is the value of E1? 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Charge is Q divided by. What is the distance here? What is the distance? X. X square. What is x square? X square is a square plus r square. So just write it like a square plus r square. Got it? So that's E1. What the direction? What is the direction of E1? I am just naming it as AB. I am naming the dipole as AB. So E1 is along BP, right? Along BP. Got it? Yeah. Now E2. I am just writing E2. Can you see E2? Okay. I am writing E2. What is the equation for E2? That will be 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Can you see it? Those in online, can you see it? See the equation. Arfat, Gobika, Neha, Riham, Sidra. Everyone. Yeah, okay. 1 by 4 pi epsilon naught. Q by, what is the charge? Charge is Q. Q divided by x square again, because the distance from minus Q to P is again x. So x square. What is x square? This one again. What is it? A square plus r square itself. That's x square. But along PA. But direction is along PA. Direction is along PA. Now you have two electric fields at this point. You have to find the total electric field or net electric field. You have to find the net electric field. You have to find the net electric field. How can you find the net electric field? Net electric field. Net electric field. Net electric field at P. Net electric field at P. What is net electric field at P? That's E. Take it as E. Take it as E. What is E? That will be vector E will be vector E1 plus vector E2. You have to do the vector sum. You have to do the vector sum. Is it okay? You have to do the vector sum because electric field is a vector quantity. So how can you do the vector sum of it? This is the point P, and E1 is like in this direction. E1 is in this direction. E2 is in this direction. Let P be in origin. Place P at origin. Place P at origin. So it will be like this. And look at this triangle. There is two angles inside the triangle. One is theta and the other is theta. So what is this angle? No. This is the outer angle actually. If this is theta, they are inside angles. Sum of inside angles will be the outside angle. So the whole angle will be 2 theta. The whole angle will be 2 theta. And when you are cutting it, you will be getting theta here and theta. That's the idea. Right? You have inside angles as theta. You have a theta here, another theta here. So the outside angle will be sum of them. That will be the outside angle 2 theta. I am not writing it. Outside angle will be 2 theta. When you are cutting it equally, outside angle, you are cutting the outside angle equally, you will get theta here and theta here. Is it okay? So you have theta and a theta. Now you can do the resolution of vectors. Resolve the vectors. How can you resolve vectors? This vector can be resolved into E1 cos theta. The side which is adjacent to theta will be E1 cos theta. E1 cos theta. You have one vector now. And what is the vector adjacent to theta here? Here you have theta. And there is another vector due to E2. So there is another vector component of E2. Component of E2 will be what? E2 cos theta. Adjacent to theta will be E2 cos theta. And there will be E1 sin theta here. E1 sin theta in this direction. And E2 sin theta in this direction. E2 sin theta in this direction. What will happen to E1 sin theta and E2 sin theta? They will get cancelled. They will get cancelled. They are cancelled with each other. One is going up, the other is going down. Then both of the forces or both of the electric fields will be cancelling each other. Joseph, is that okay? Okay. What about here? What about here? You can just take the magnitude of E1 and the magnitude of E2 equal. Magnitude of E1 and magnitude of E2 as equal. Both of them are equal. You can just take it as E1. You can just take it as E1. Why is that? You are taking E for the net electric field. That's right. This is not the net electric field. This is electric field due to Q1. Sorry, electric field due to plus Q. This is electric field due to minus Q. So I am just taking it as E1. Is that okay? So what is E? The net electric field. E is net electric field. E1 plus E2. E1 plus E2. What is the component of E1 that is in this direction? That is contributing to net electric field. That will be E1 cos theta. And then next one, E2 cos theta. Both of them are equal. Both of them are equal. So you can replace E2 with E1. Or should I write the next step also? Okay, E1 cos theta plus E1 cos theta, that will be 2E1 cos theta. 2E1 cos theta. 2 into, what is E1? What is E1? E1 is this one. 1 by 4 pi epsilon naught. E1 is the electric field due to plus Q. Isn't it? 1 by 4 pi epsilon naught. Q divided by, what is the distance x? X is a square plus r square. That's it. X square is needed. So x square will be equal to a square plus r square. That's it. So This is E1. Now you have to write cos theta. What is cos theta?
A by
I'll skip this and just write cos theta directly. What is cos theta? Yeah. From this triangle, you can see cos theta will be adjacent side by hypotenuse. What is adjacent side here? What is adjacent side? Adjacent side is A. So A divided by what is hypotenuse? X. A divided by X. And cos theta is equal to A divided by who is X? What is the value of X? A square plus R square all raised to 1 by 2. So that's X. A square plus R square all raised to 1 by 2 is the value of X. Joseph? Now, what is X? A square plus R square all raised to 1 by 2. That's X. Is it okay? Then you can substitute for cos theta here. That will be A divided by A square plus R square all raised to 1 by 2. Are you writing with me? Okay, okay, that's good. And just look here. I will round, which is the quantities which are familiar. I will round the quantities which are familiar. Here you have a 2. Here you have a Q. And here you have a A. So what is that? 2QA or Q2A. What is Q2A? That's P, dipole moment, electric dipole moment. Q2A is what? Electric dipole moments. That's electric dipole moment. Got it? So you can just substitute that value. 1 by 4 pi epsilon naught. Q2A is P divided by, now you have A square plus R square into A square plus R square raised to 1 by 2. That means here you will have a 1 and here you have a 1 by 2. So that means 1 plus 1 by 2 will be the power. That will be 2 plus 1. 3 by 2 is the power. Is it okay? So you can write A square plus R square all raised to 3 by 2 as power. Okay? And we are doing the assumption. What is the assumption? If A is very much less than R, this term A square plus R square all raised to 3 by 2 can be approximately written as, you can just neglect A square.
Sir, R is greater than
Yeah. Yeah, it can, but what is this? What is this thing? This is the electric dipole. What is the definition of dipole? Two equal and opposite charges separated by a small distance. They are very small distance. They are separated by a very small distance. That means A is very less. Okay. So approximately equal to, you can neglect A square, that will be R square all raised to 3 by 2. R square all raised to 3 by 2. What is R square all raised to 3 by 2? R square all raised to 3 by 2 will be R raised to 2 into 3 by 2. 2 into 3 by 2, 2 will be gone. That will be R cube. That will be R cube. So the equation will be 1 by 4 pi epsilon naught P by just R cube here, right? Just R cube here. P by R cube. This is the electric field at P on the equatorial line. This is the electric field at P on the equatorial line. Got it? What is the direction of it? You have to specify the direction of this electric field. What is the direction of this electric field? What is the direction of this electric field? The direction will be this electric field. The net electric field is towards the left. Net electric field is towards the left. Right? Right? What is the direction of electric dipole moment? In this case, what is the direction of dipole moment? Dipole moment is towards right, minus q to plus q. So now this electric field is towards left. That means it is against the dipole moment. It is against the dipole moment. It is against the dipole moment. That means you can put a minus p cap there. You can put a minus p cap there. What is the use of that minus p cap?
Light.
Direction. It is showing the direction. the direction is opposite to dipole moment. Which one? Where did you get P? Minus P cap. What is the direction P cap?
Towards.
Not towards or away. It is from minus Q to plus Q. What is the direction of net electric field here? That's from right to left. That means it is against or it is opposite to the direction of dipole momentum. Then you can write it like this. E equatorial is equal to minus 1 by 4 pi epsilon naught P by R cube P cap. This is the equation. Okay? In the equation for electric field due to a dipole at the equatorial line, there will be a minus there, There will be a minus sign and there is no 2. For axial line, there was a 2, and for equatorial line, there is a minus and a no 2. So you can combine them like this. E axial. How can you get E axial from this one? How can you get E axial from this one? You have to put a minus first. Then only this minus will be cancelling out. Minus into minus will be plus. So minus into 2. When you are multiplying 2 with this one, that will become 1 by 4 pi epsilon naught 2 P by R cube. Then now you get axial electric field. So minus 2 into E equatorial will give you the equation E axial. This is the important equation. E axial is equal to minus 2 into equatorial.
So, minus 1 by 4. And then minus P, then it minus go to that.
Equatorial line.
No, the minus comes.
Where did the minus come?
No. The minus will be there always.
Minus is there. Minus is there. Which is
Or
the-
it's there. Because minus, right, that's 1 by 4 epsilon, P by R is minus P.
that will be okay. That also is okay. Minus P cap, that's a minus sign. Minus sign can be taken out. All these terms are multiplications. 1 by 4 pi epsilon naught into P by R cube into P cap. So that minus can be taken out. No problem. If you are writing that minus where it is, that will also be okay. If you want to take it out, that will also be okay. Okay, so this is the relation between axial electric field and equatorial electric field. Axial electric field and equatorial electric field. E axial will be equal to minus 2 E equatorial. What is the ratio between them?
Yeah, actually.
E axial divided by E equatorial. E axial divided by E equatorial will be minus 2. E axial divided by E equatorial will be minus 2. Now we have completed the second derivation. What is the third one? Third one, torque on dipole. Third one is torque on dipole. We have to do dipole in a uniform electric field, right? Torque on dipole. What is the third one? Is the second derivation okay? Everyone? Arfat, Gobiga, Neha, Riham, Sidra. Is the second derivation okay?
Yes, sir.
Okay. Okay. Okay, Neha. Now I am going to the third. Torque, the third one. Torque due to a dipole. Due to a dipole. Torque due to a dipole, no. Torque due to an electric field, actually. Torque
On dipole.
on the dipole due to electric field. Torque on a dipole. That's the better word. Torque on a dipole. Torque on a dipole. How can we see that torque on a dipole? This is electric field. This is electric field. Right? This is electric field. And what is the property of this electric field? This electric field is actually uniform. This electric field is uniform. Now you have a dipole which is placed in this field, and you have a plus q here and minus q here. Plus q here and minus q here. What is the distance between them? What is the distance between the plus q and minus q? That will be 2a. That will be 2a. And you can name them. You can name the dipole. Like this is A and this is B. If you are just extending A like this and you are extending B like this, you will get a perpendicular here. And call it as N. Call it as N. Is it okay? Call it as N. Now, take this angle. Take this angle. Take this angle as theta. Take this angle as theta. Now, how can you find the torque on a dipole? This dipole is now in an electric field. That means there will be a force acting on this charge due to this electric field. The force at this is plus q actually. This is plus q actually. The force acting here will be in this direction, in the direction of electric field. That force will be F is equal to plus QE, plus QE, plus QE. Right? Now the force will that will be experiencing on minus Q will be F is equal to minus QE. That's in opposite direction. So there is two forces equal and opposite direction. There is two forces which is acting equal and opposite directions on a dipole. And what will happen to this dipole? It will get rotated. The dipole will get rotated. Dipole will get rotated. So you can find the torque acting on it. You can find the torque acting on it because the torque is rotating it. Torque is the one which is rotating it. So torque is equal to force into perpendicular distance. Force into perpendicular distance is the equation for torque. So torque is equal to force into perpendicular distance. What is force here? QE is the force. You can just take it as QE. QE, magnitude of force. QE into perpendicular distance. What is the perpendicular distance here?
BN.
Here you have B and here you have a point N. This is the perpendicular distance between the two forces. Right? Bn is the perpendicular distance between the two forces. This is one force, this is the second force. So Bn is the perpendicular distance between the two forces. That means QE into Bn. Now you have to find Bn. How can you find Bn? How can you find Bn? Using the identity cos theta. Bn can be found out from cos theta. Yeah, sin theta. Then only you will be getting the opposite side. Then sin theta, using sin theta. What is sin theta? Opposite side by hypotenuse. What is opposite side? Bn is opposite side. What is hypotenuse? Hypotenuse 2a. Hypotenuse is 2a. Now you can write Bn. What is Bn? Take this 2a to the other side. That will be 2a sin theta. You will get 2a sin theta. Are you getting it? 2a sin theta. Now you have Bn. Then what is tau? Tau is equal to QE 2a sin theta. There is familiar terms that we can see now. Q2a. Q2a. What is Q2a? Q2a is electric dipole moment P. That's electric dipole moment P. Now you have electric dipole moment P. Got it? Now the equation tau is equal to Q2a is P, right? So P E sin theta is the equation. This is the magnitude, right? Now you have to write that in the vector form. Tau is equal to P E sin theta is in the form A B sin theta. A B sin theta is A cross B. A B cos theta is A dot B. A dot B. A B sin theta is A cross B. Just like that, P E sin theta is P cross E. P cross E.
Sir,
That's
AB sin theta is A cross beta. So AB cos theta.
A dot B. That's dot product. This is cross product or vector product. Now, this dipole momentum, it's a vector, and electric field, another vector. And when they are multiplied with each other, you are getting another vector. The result is a vector, then it is a vector product. The result is a vector, then it is a vector product. Now, what will be the maximum tau? Tau maximum. Tau maximum is when? When theta is maximum, theta is sin theta is maximum. Theta is 90 degree, sin angle will be maximum, sin angle will be 1. That means tau is equal to PE. Tau is equal to PE. This will be the maximum tau. Maximum tau. What will be the minimum tau? T maximum, sorry. T minimum. What is the T minimum? When theta is equal to 0 or theta is equal to 180 degree. Just you can take it as theta is equal to 0 also. And what is theta is equal to 0? When theta is equal to 0, what will happen? Tau will be PE sin 0. PE sin 0. That will be tau mean value. Minimum tau will be 0. Value of minimum tau will be 0. And what is sin 180? Also 0. Sin 180 is also 0. Then when you are giving sin 0 and sin 180, you will be getting 0. So that means torque minimum will be having a value 0. Here we have two cases of equilibrium. Two types of equilibrium are there. What are the two types of equilibrium? What about this derivation? Is derivation okay? Arafat, Gobika, Neha, Riham, Sidra.
Yes, yes, sir.
What about you, Sidra?
Yes.
Okay. Riham? Is it okay, Riham? Okay. And there is two cases of stable and unstable equilibrium. Stable equilibrium. Stable equilibrium. And unstable equilibrium. Unstable equilibrium. What is stable equilibrium? When theta is equal to 0, that's contributing to, that's corresponding to stable equilibrium. When theta is equal to 180 degree, that will be unstable. Both of them are equilibrium, cases of equilibrium. One is stable and the other one is unstable. If electric field is in this direction and you have a dipole here, this is minus q and this is plus q. Both of them are in the same direction now. Dipole moment is in the direction of minus q to plus q. Now you have dipole moment in the direction minus q to plus q. Electric field is in the direction, the same direction, towards left to right. So now both of them are in the same direction. That means theta is equal to 0. If theta is equal to 0, this is called stable equilibrium. No, this is parallel. This is also parallel. Stable equilibrium means what? This is parallel. 0 degree is corresponding to the word parallel. So unstable equilibrium is theta is equal to 180 degree. What is that? Yeah, that's anti-parallel. Anti-parallel. That's anti-parallel. How can you get anti-parallel? If this is the electric field and you have a dipole like this, but dipole is minus q to plus q like this. What is the direction of dipole moment? Direction of dipole momentum will be from minus q to plus.
So when the surface dipole goes back, or
This is equilibrium actually. Dipole will not be rotating. Got it? There is no torque on it.
so Q will try to go other direction.
No.
Minus Q will try to go other direction.
That's why this is called unstable. This is now in an equilibrium, but that equilibrium is unstable. Good. Now, what is the next derivation? Is this one okay? Everyone, is this one okay? What is the next derivation then? What is the next derivation? Work done to rotate a dipole. That's in the second chapter. Potential energy of dipole, second chapter. Proof of Gauss's law. Proof of Gauss's law. Proof of Gauss's law. How can you prove Gauss's law? That's the equation. That's the question. How can you prove Gauss's law? Proof of Gauss's law. Fifth derivation, isn't it? Fifth derivation. Proof of Gauss's law. Proof of Gauss's law. What is Gauss's law? What is Gauss's law? It is about electric flux. It is about electric flux. Net electric flux that is coming out of a closed surface will be 1 by epsilon naught times the charge enclosed by that closed surface. That's Gauss's law. This is the expression for Gauss's law. Now we have to derive the equation for Gauss's law. How can you derive this equation? You can take a sphere like this. You can take a sphere like this. Do it with me. You can take a sphere like this. This sphere is actually a charged sphere, right? This is a charged sphere. And you are just taking a small area here. What is that small area? That small area will be ds. S will be the total area. S is the total area. Then ds will be the small area. The center point of the sphere is marked. This is the center of sphere. This is the center of sphere. And what will be the direction of electric field from this through this ds? Electric field will always be perpendicular to the surface. It will be perpendicular to the surface. It will be perpendicular to the surface. Okay? And note the surface is charged. There is a slight difference in it. There is a charge Q1. There is a charge point Q. Point charge. There is a point charge at the center. There is a point charge at the center. We are considering a surface, a sphere around it. There is a charge, point charge, and we are considering a sphere around it. Okay? Now, due to this charge is positive. Let this charge be positive. Then what will be the direction of electric field? Electric field will be in this direction, will be going away from it. If that's a positive charge, electric field will be going away from it. That means electric field will have this direction. Okay. What is the direction of area vector? What is the direction of area vector? Direction of area vector. Area vector is always perpendicular to the surface. It will be always perpendicular to the surface. And it is always perpendicular to the surface. That means area vector. You can call it as ds. Area vector, ds. ds. Area vector ds will be perpendicular to the surface. Now you can see that both electric field and area vector are in the same direction. They are in the same direction. Now you can find the small flux that is coming out of this small surface area. Small flux due to coming out of this small surface area. Write that equation. What is the small flux? Small flux, value of small flux through ds. Small flux through ds. Through ds. Small flux through ds. What is it? Small flux d phi. Small flux d phi. What is the equation? EDS. What is that equation? EDS. E dot ds. EDS. E dot ds. Isn't it? This is the small flux that is coming out of this small surface. What is the total flux then? What is the total flux coming out of the sphere? Total flux through the sphere. Total flux through the sphere. That will be integrate it. Just integrate it. You have a small small flux that is coming through the ds, area ds. Just integrate it, you will get total flux through the sphere. Are you getting an idea? When you are integrating it, you will get total flux as pi. When you are integrating this small flux, when you are integrating the small flux, you will be getting the total flux. Okay, so the total flux will be equal to closed integral, because this is a closed surface, right? Closed surface. So, closed integral of E dot ds. E dot ds. What is E? What is E? You can see that E is what? E is electric field, because this is a point charge. This is not varying. This is not varying. This is what? It's a constant. You can take the electric field out of the integration because it is a constant. Integral ds. What is integral ds? You have a small surface area, that is the ds. The value is ds. When you are integrating it over the closed surface, what you will be getting? You will be getting the total surface area of the sphere. That will be total surface area of the sphere. What is the total surface area of the sphere? What is the total surface area of the sphere? Surface area of the sphere, what is it? 4 pi r square. That will be 4 pi r square. It is the surface area of sphere. Surface area of sphere. Surface area of sphere. So, closed integral ds will be 4 pi r square. You can write it like this. You can write surface area of sphere here. The equation will be what? 5 equal to, what do you have here? That's E. E into, what is it? What is E? You can write E then. E is what? 1 by 4 pi epsilon naught. E is due to this point charge. Its value is Q. So 1 by 4 pi epsilon naught Q divided by distance square. The distance to ds will be what? The radius itself. Okay. So Q by r square. Q by r square. Q by r square is the electric field. Okay. And what is integral ds? Integral ds is 4 pi r square. Integral ds is 4 pi r square. So 5 will be 4 pi and 4 pi is cut from it. R square is cut from it. So Q divided by epsilon naught will be the equation for 5. Q divided by epsilon naught. This is the equation for 5. What is 5? That's the electric flux through a closed surface. Electric flux through a closed surface. Now this is the proof of Gauss's law. This is the proof of Gauss's law. Everyone, is it okay? Is this good? Can you do this and now on? Sidra, okay, Sidra, Riham. Arfat, okay. Neha, okay. What about you, Riham? Okay, good. Now, this is what? The proof of Gauss's law. Yeah. You can take a break. This is 5:30. That's 5:30. You can take a break and come back after 10 minutes. Is it okay? Please come back after 10 minutes. You can take a small break. Take a small break. Come back after 10 minutes. Is it okay? Arafat, Gobiga, Neha, Riham, Sidra, everyone here? Are you all here? Okay, Neha, okay, Gobiga. What about the others? Sidra, okay, okay, Sidra. Okay, then look at the next derivation. Look at the next derivation. What is the next derivation? Electric field due to a long wire. Electric field due to a long wire. For this, you have to draw a long wire. You have to draw a long wire. This wire is uniformly charged and it is infinitely long. This wire is uniformly charged and infinitely long. They are the conditions. Now you have to find the electric field. You have to find the electric field at this point. You have to find the electric field at this point P. You have to find the electric field at this point P. How can you do that? You have to contain that point into a Gaussian surface. You have to create a Gaussian surface here. That Gaussian surface for a line, a linear charge. That Gaussian surface for a linear charge will be in the shape of a cylinder. That Gaussian surface in for a linear charge will be in the direction of, sorry, in the shape of a cylinder. Got it? In the shape of a cylinder. Look at this point. Look at this point P. What about this point? If you are taking a small area here, if you are taking a small area here, that small area is ds. That small area is ds.
So,
Yeah.
should we have test here?
Right. I asked you to do it. Haven't I messaged you earlier as a personal message? Derivation test. Derivation test. If you get time, if we have enough time, we will do that. Otherwise, we will do it from home. I will give you a question and you will do the derivation and send it to me.
So we have break like 6 to 6:30 something, right?
Yeah.
You will take it in
6:30 to 6:40 will be the break.
up to
10-minute break before the next session.
okay.
Now look here. Look here. And what can you see from here? This is ds, area vector. Area vector. Area vector will always be perpendicular to the surface. And what is the direction of electric field, which is through this P? Electric field at this P. Electric field at this P. This is positive. Positive charge. So electric field at P will be in this direction. Can you see that? Electric field at P will be in this direction. That means the electric field at P and the area vector at P both are in same direction. That means theta is equal to 0.
So Coulomb's law is that proportionality, right?
We can do that later. Okay. That theta is equal to 0. Theta is equal to 0. Okay. What about a point here? The electric field will be in this direction because this is positive charge. Positive charge will be away from it. Electric field will be away from the positive charge. So electric field will be in this direction. And what about area vector? Area vector is always perpendicular. Always perpendicular. That means area vector ds will be in this direction. ds will be in this direction. It is perpendicular. Now the theta is 90 degree. Theta is 90 degree. What is 90 degree signifies? What is 90 degree signifies? Flux is what actually? What is the equation for flux? EA cos theta, right? E dot A or EA cos theta. Now, what is theta? 90 degree. Cos 90?
Cosine is 0.
0. Cos 90 is 0. That means there will not be any flux through this base. That's the meaning. Flux will be coming out of this surface only through the curved surface. So that's very important point. Flux only through the curved surface. Through the curved surface. Flux only through the curved surface. Curved surface. Now, we can find the value of electric field. We can find the value of electric field. What will be the equation? What will be the equation? What will be the equation? Two equations are for flux. First equation is integral E dot ds is equal to phi. And the second equation, phi is equal to closed integral E dot ds. The next equation is from Gauss's law. Q by epsilon naught. There are two equations for flux. One is this, and the second one is, we have written it. This is first equation and this is second equation. They are equal, right? They are equal. Both of the equations are equal. So you can equate them. How can you equate them? Closed integral E dot ds will be equal to Q by epsilon naught, like this. Electric field is a constant. You can take that out. Electric field is a constant. You can take that out. Closed integral ds is equal to q by epsilon naught. What is closed integral ds? Closed integral ds is, this is the small surface. This is small surface. They are asking you to find the total surface through which flux is passing out. That means curved surface area. Only through curved surface area flux is passing. So this is curved surface area. This is curved surface area. What is the curved surface area of a cylinder? 2 pi RL. That will be 2 pi RL. L is the length of the cylinder. L is the length of the cylinder. Got it? Now you have equation like this: E into 2 pi RL is equal to Q by epsilon naught. You have the equation for E. E is equal to 1 by 4 Q by 2 pi RL epsilon naught. You have a familiar term here. What is that? Q divided by L. You have a familiar term here, that is Q divided by L. What is Q divided by L? Q divided by L is what? That's sigma. No, that's lambda. Q by L is lambda. Who is lambda? Who is lambda? Linear charge density. Lambda is linear charge density. What is lambda? That's linear charge density. Lambda is linear charge density. Okay, so you can rewrite it as lambda divided by 2 pi epsilon naught r. 2 pi epsilon naught r. This is the equation for electric field at a point due to a line charge, which is uniformly charged and infinitely long. This is the electric field at a point P due to a line charge, lambda by 2 pi epsilon naught r. If you want a vector form, that vector form will be E is equal to lambda divided by 2 pi epsilon naught r into r cap. R cap is radially outwards. Radially outwards is this dash. Radially outwards is this dash. Radially outwards. Got it? Everyone, what about this derivation? Is it okay? Is this derivation okay? Is this derivation cool? Okay. Then the next one.
Sir, question.
There any problem with any steps? Once you have studied this step, the same step will be used in the coming derivations. The same step can be used in the coming derivations. That is very simple to do. If you are okay with this step, okay. You have to find the Gaussian surface. That's all. Once you have selected the Gaussian surface, everything will be okay. Every other values will be okay. Can I move on? Okay. Then the seventh one. What is that? Electric field due to a sheet, charged sheet. Electric field at a point due to a charged sheet. Electric field due to a charged sheet. I have a charged sheet here. That charged sheet is uniformly charged. It is uniformly charged. What is it? It is uniformly charged and it has dimensions of infinite dimension. It has infinite dimension. That means it has infinite length. Now you have to find the electric field due to a point here. Electric field due to a point here. You have to consider a Gaussian surface. How can you consider a Gaussian surface here? In the form of a cylinder. You have to consider a Gaussian surface in the form of a cylinder. Like this.
Yeah.
Right? This is now a cylinder. We have considering a cylinder as the Gaussian surface. Now what will be the direction? you are just taking a small area here. That small area is ds. The area vector will be coming out of it. It will be perpendicular to the surface. Area vector will be perpendicular to the surface. That means ds will be perpendicular to this surface. Got it? ds will be perpendicular to the surface. This is positive charge. So this is positive charge. That means electric field will be away from it. So electric field will be in this direction also. Electric field will be in this direction also. Got it? And what about here? What about on the curved surface? On the curved surface, what will happen? On the curved surface, electric field will be in this direction. Electric field will be in the same direction as that of the electric field. Because this is positive charge, electric field will be going away from it. And what is the direction of ds? Direction of small surface, that is vector, area vector. What is the direction of area vector? Area vector will always be perpendicular to the surface. So area vector will be in this direction. This is the direction of ds. What is the angle between ds and e? This angle between ds and e will be 90 degrees. That means there will not be any flux through it. There will not be any flux through the curved surface. Flux is only through the face. Only through the face. What about here? What about here? Here, the direction of electric field will be in this direction. ds also is perpendicular to the surface. That means ds will be in this direction. And what about e? What about e? Electric field. Electric field will also be in this direction. So electric field will be in this same direction. Now you can see theta will be 0 here. Theta is 0 also here. So where do what is the status of flux? What is the status of flux? Flux will be through the faces. Through the faces. Flux will be through the faces. Flux will always flux is going out of this Gaussian surface through the faces. There is no flux here or here or here or here. No flux through the curved surface. Got it? Because electric field and ds is at an angle 90 degrees. So there is no flux through the curved surface. Got it? Now what are the steps? What are the steps? Flux is, total flux is closed integral E dot ds. And according to Gauss's law, what is flux? Flux is Q by epsilon naught. This is the first equation. This is the second equation. You can combine them equations. You can combine them. How is that? Closed integral E dot ds will be equal to Q divided by epsilon naught. Got it? Right? Okay? Everything set? What is the next one? E can be taken out of the integration. Closed integral ds will be Q divided by epsilon naught. Okay? What is closed integral ds? Closed integral ds. Here you have a small surface ds, right? When this small surface is integrated, you will be getting this whole surface A, right? You will be getting this whole surface A and shading it. You will be getting this whole surface A, and there will also be another A here. There will also be another A here. There will be flux through this area. There will be flux through this area also. So, what is integral ds? That will be A plus A, which is 2A. Integral ds is 2A. So, E into 2A is equal to Q by epsilon naught. And electric field is equal to Q divided by 2A epsilon naught. You have a familiar term here. You can see a familiar term here. What is that familiar term here? That's Q by A. What is Q by A? That's sigma, surface charge density. What is Q by A? Sigma. What is sigma? Sigma is surface charge density. Surface charge density. Surface charge density. That's sigma. Got it? So you can replace Q by A with sigma. Then you will be getting equation for electric field as sigma divided by 2 epsilon naught. Sigma divided by 2 epsilon naught. As you can see, there is no term of R in it. there is no term of distance in this equation. That is, electric field due to a sheet, a uniformly charged sheet is independent of distance. Electric field due to a charged sheet is independent of distance from it. Got it? Okay. We want to go. You said that you want to go after sunrise. That's okay. Okay. And what about the next one? What will be the vector form of this? If you want to write the vector form of this, just add n cap. Just add n cap. Or a unit vector which is in the direction of electric field. Okay. Is this okay? This 7th one, electric field due to a charged sheet is okay? Everyone? Arafat, Gopika, Neha, Riham, Sidra. Guys, is it okay? Okay, okay, okay. I'm going to the next one. What is it? Next one, 8th one. What is the 8th one? Electric field due to a charged shell. Electric field at a point due to a charged shell. Due to a charged shell. Charged shell. Charged shell. What is the charged shell? This is the charged shell. And it is positively charged. It is uniformly charged. Positively charged, it is uniformly charged. What is the radius of it? Radius of that shell is capital R. And I am taking a point here. The point here is P. The point here is P. And considering a Gaussian surface that is containing this point P, then only we can derive the derivation for electric field. Equation for electric field. Now I have to consider a small surface here. That small surface is ds, and the area vector will be in this direction. The area vector will be in this direction. Area vector will be in this direction. That is the direction of ds is this. And what about electric field? What about electric field? Electric field will always be perpendicular. Not always be perpendicular. You cannot say it like that. Electric field will be away from it. That's the correct word. Electric field will be away from it. So electric field will be away from this point.
That is part of the electric field.
It is property when you are considering conductor. This is not conductor. This is a Gaussian surface. It is not real. Got it? So you can just say it like that. Electric field will be away from the positive charge towards the negative charge. That's all. Okay. So this is electric field. This is electric field. Got it? And the angle here is theta is equal to 0. So you can have that whole area. Wherever you are taking this point, everywhere there will be electric field and the area vector having an angle theta is equal to 0. So the whole surface, through this whole surface, there will be electric flex coming out of this whole surface. So what is our derivation? What will be our derivation? We have two equations. Closed integral E dot to ds will be equal to 5, right? That's equal to 5. So 5 has this equation. Flex has this equation. This is the first equation. And the flex has another equation according to Gauss's law, that is Q by epsilon naught. You can combine them. Integral E dot to ds is equal to Q divided by epsilon naught. You are combining this equation. And electric field, that we have to find it. Closed integral ds is equal to Q by epsilon naught. What is the closed integral ds? Closed integral ds is what? ds is this small surface, right? When you are integrating it, you will be getting the whole surface area of the sphere. Whole surface area of the sphere. What is the whole surface area of the sphere? 4 pi r square. Not this r square. This r square. No. Small r square because we are considering the Gaussian surface. This small area is on the Gaussian surface. So you have to consider the whole surface, whole Gaussian surface has a radius r. Okay. So r square, 4 pi r square is ds. and you have E here, E into 4 pi r square is equal to Q by epsilon naught. And what is the value of E? E is 1 by 4 pi, take this epsilon naught here, 1 by 4 pi epsilon naught, Q divided by r square, Q divided by r square. What does it mean? It's like this whole charge is concentrated at this center. It's like the whole charge is concentrated at this center. What is this equation actually? What this equation is used for? This equation is actually used for the electric field due to a point charge. This equation is used for the electric field due to a point charge. This is the equation for electric field due to a point charge. And this is the same equation for a shell. That means for a shell, for a conducting, for a charged shell, the charge is as if it is concentrated at the center. The charge is like point charge. Charge is like point charge, it is concentrated at the center. It is experiencing at this point like that. It is experiencing at this point B like that. Like the charge is concentrated at the center. Okay? But is the charge actually at the center? No, it is around the, it is on the sphere. It is on the sphere, but this is the equation which is used for the electric field due to a point charge. So the same equation means is like the charge on a charged shell is like it is concentrated on the center. Okay, that's and now this is the equation for E. Now this is the point on the outside, right? This is the point on the outside. Point on the outside. Point on outside. This is the equation for the point on the outside. What is the point on point on the surface? Equation for point on surface. What will be the equation? Point on surface. If the point is taken on the surface, that means this r will be, small r will be, Gaussian surface will be equal to the sphere itself. Gaussian surface will be equal to the sphere itself. That is small r is equal to capital R. Then the equation will be E is equal to 1 by 4 pi epsilon naught Q divided by capital R square will be the equation. Capital R square will be the equation. Got it? And what about inside of it? Point on the inside. Point on the inside. Point on the inside. What is the point is on inside? What will happen if this is the sphere and you are taking a point inside? This is the radius of the sphere, and you are taking a point inside. You can draw the Gaussian surface even then. What is the Gaussian surface? This will be the Gaussian surface. This is the Gaussian surface. If this is the point P, what is the electric field at P? How can you do that? Electric field at P. Just look here. By Gauss's law, phi is equal to Q divided by epsilon naught. What is this Q? Charge enclosed. That is Q. What is Q? Charge enclosed. What is charge? Charge is on the surface. Charge is on the surface. So Q is what? Q is charge enclosed. What is Q? Charge enclosed. What is charge enclosed? The charge enclosed. What is the charge inside the Gaussian surface? Zero. There is no charge inside this yellow Gaussian surface. This Gaussian surface is shown, seen as yellow color. In yellow color, it is represented in yellow color. So there is no charge inside that Gaussian surface. That means Q is equal to 0. If Q is equal to 0, flux also will be equal to, electric field also will be equal to 0. Electric field also is equal to 0. So electric field at a point inside the shell. Electric field at a point inside the shell. Electric field at a point inside the shell will be E is equal to 0. Electric field inside the shell, it will be 0. Electric field inside the shell will be 0. So that's the 8th one. Electric field due to a charged shell. We have completed it. Electric field due to a charged shell.
One more.
Which one? No, there are others. Work done due to dipole is the. This is actually the first chapter, main derivations of first chapter. These are the main derivations of first chapter. Sometimes in some schools they may teach this work done due to a dipole in first chapter. What about you? Have you studied work done due to a dipole in first chapter or second chapter? I taught you it in the second chapter. Work done due to a dipole. Okay. Some schools may take it in the first chapter. That will be okay. Work done due to a dipole and potential at an axial line, potential at an equatorial line, like that. Can we move to the other derivation parts? The derivations which are in the second chapter, can we move to that? Do you need the test to be right now or when if you are at the home? What do you prefer? Do you want to try? Do you want to try any of this? Do you want to try any of this? I will give you different derivations. I will give you different derivations. I will give you different derivations. I will start with alpha. I will start with alpha. Only because Arfat is the first one on online. That's why. Arfat, I will give you a derivation. Just try to do that derivation and just send that to me.
Okay, sir.
Okay. The derivation is electric field due to a charged sheet and draw its graph also. Electric field due to a charged sheet and draw its graph also. That's for alpha. Electric field due to a charged sheet. Is that okay?
Yeah.
Yeah, do that. And for Gobiga, electric field due to axial, electric field at a point on axial line. Gobiga, electric field at a point on the axial line. You got it? Yeah, okay. Do that. And Neha, electric field at an equatorial point. Neha, electric field at an equatorial point. Do that, Neha. After you have done it, just send that to me. Send a photo to me. And Riham, electric field due to a long wire. Electric field due to a long wire. Do that, Riham. Electric field due to a long wire. And also draw a graph for the electric field. Graph for the electric field and distance. Riham. Is that okay? Okay, Riham. Then Sidra is the Sidra. Do this one. Torque on dipole. Sidra. Torque
Yes,
on dipole.
Okay.
Okay. Do that and send that to me. And for you, do electric field at equatorial point. Electric field at an equatorial point. Electric field at equatorial point. Electric field due to a shell. Electric field due to a shell. Every case. Every case. And electric field due to a long wire. No. You also do electric field due to equatorial. Electric field due to equatorial. Both of you are doing, Joseph and Jovita doing electric field due to equatorial points. And let's see, you are doing electric field due to a shell. Okay, do that. Okay, do that. And after that, you have to send that to me. After you have completed it, please send that to me.